Hey everybody, grade 9 math, unit 7, similarities and transformations. And this one, we're going to go over the concepts of symmetry, tessellations, and rotational symmetry. Really exciting stuff. These concepts and the math they represent are important because they have really cool applications in the real world, not just math class. And I'm telling you, I like math class, so these applications better be pretty good. If I look at this triangle here, what we're going to do is we're going to draw a line right down that dotted line. Nailed it. First try. We can see that we could fold that triangle over the red line and it would meet corner to corner. In fact, we could do it 3 different ways, from that corner to that corner and there. So we would say that this has an order, or the number of ways that we could fold it on itself and not have any gaps or any parts hanging over. We could say that this has an order of 3. 1, 2, 3. Now, if we look at the square, squares being what they are, basically we've got a line there, close, a line there, still close, a line there, nailed it, and a line right there, pretty close. So we would say that this would have an order of, can you guess it? That's right, 4. 1, 2, 3, 4. Now, some shapes don't have a way of being symmetrical. So it's not that they're not cool. We just shun them and make them feel bad. Kidding. They have every right to be, proud polygons. Okay, so here's what we're going to look at as far as symmetry goes and the real world. And what is it that makes a beautiful face beautiful? Well, they're symmetrical. This means that one half of the face looks exactly like the other half. It's almost as if you could put a mirror running from the top of their head to the bottom of their chin, and the reflection will be exactly the same, a mirror image. That's symmetry. Symmetry in nature is something that humans have come to regard as something being pleasing and beautiful. But deeper than that, symmetry in nature has an evolutionary function in that symmetrical organisms have a better chance of surviving than asymmetrical organisms. Now, there's 2 types of symmetry in nature. There's rotational symmetry and bilateral. So when we say rotational, we basically mean that we could take, and we'll just get a line here, we could take a center point of an object, of that tiger lily, starfish, and the snowflake. And basically, you could draw a line from one arm or limb or petal to the center point and then rotate it, and it would fall exactly on another one and rotate it. And these guys would have their own numbers of orders. So as you rotate around the clock, it just falls on itself. And we see this all the time in nature. So look at the starfish. I mean, it's got 5 arms. And so it would have an order, or a rotational order of 5. Not a symmetrical order of 5, a rotational order of 5. And the snowflake would have, what do we got here? We got 1, 2, 3, 4, 5, 6. So a rotational order of 6. The interesting thing about a starfish is that years ago, fishermen in Newfoundland and Labrador were frustrated that the starfish were getting into lobster traps and eating all the lobster food, and they weren't catching any lobsters. So they thought they'd do a cool thing, and they pull up these starfish and chop them up into little bits. Ha ha! Take that, starfish, and throw them back in the ocean. Well, guess what? Starfish have regenerative properties. So from one limb, the starfish could regenerate the other 4 limbs. So instead of getting rid of starfish, almost overnight, those poor Newfoundland fishermen created a tsunami of starfish. There you go. We didn't know that until they did it. Another interesting fact about snowflakes is that every snowflake's nucleus is a mote of dust. So a snowflake isn't pure water. It clings to a piece of dust and it forms a crystal. And also interesting about tiger lilies is they're not really orange. A bee and other insect species that look at flowers, they look at them through the UV light rays. And a tiger lily is actually blue. No kidding, check it out, Google it. So that's rotational symmetry, meaning that around a central point, an object will tessellate, or not tessellate, an object will fall onto itself without any gaps or missing parts. The other type, and the type like you and me, is bilateral symmetry. That means we can take a vertical line and one half will look just like the other half, like the mirror image of my girlfriend above. And here, this harp seal, bilateral symmetry, and the shark, bilateral symmetry. We see it in insects, we see it in all kinds of little creepy crawlies, right? Now, why is that? Well, here, I'm not sure if we can explain why, but if you're bilaterally symmetrical, it means that you have the ability to go forward and backwards and sideways. Not unlike a jellyfish, but you control your movement according to a central nervous system, right? So if you have bilateral symmetry like humans and beetles, you have a brain and neurons. So you can react to heat and light and pain and hunger and all that sort of things, and you can move to go get out of danger or to find nutrition, right? If you have radial symmetry, then you don't have a brain, but you do have neurons, which means you can react to your environment, but you're just reacting. You're not deciding anything, you're just reacting. So for example, anyway, you get the idea. Now, we've taken this idea of symmetry into pop culture, especially business culture, and we said, well, these ideas are appealing to us, this idea of symmetry. So these logos are good examples of different lines of symmetries, and we've got McDonald's and British Petroleum and Red Bull and all of these. And basically, what we could do with each one is we could take, here, let's get a line, and let's make it a blue line. And we could draw a line of symmetry basically through each of these in many different ways. And we can just see, oh, missed it, got it, missed it. Red Bull, Chevrolet, Honda, Shell. Like, I'm not going to say all these names, but you get the idea. Some are rotational symmetry, some are bilaterally symmetrical. But the idea is they're popular because they make sense. Now what we're going to do is we're going to talk about this idea of rotational symmetry. And here we've got a guy with a pinwheel fan, and it's going round and round and round. That's the idea. When we say round and round and round, oh, let's switch to a pencil here. Okay. When we say around and around and around, we mean around 360 degrees. Okay. So in this example, if we go, and now we're going to go around the other way just because I showed it that way. As we go around from A to B, B to C, C to D, we see that at 90 degrees, the fan blades are exactly symmetrical. So they've fallen right onto themselves. So let's just highlight this sucker because it's super important. Any object or shape is said to have rotational symmetry if it looks exactly the same at least once during a complete rotation through 360 degrees. So in a full turn, there are precisely 4 positions when the windmill is exactly the same. Because of this, we say it has a rotational symmetry of 4. Because 4 times within 360, it's going to be symmetrical. So here's another one. Let's say we've got a square, okay? And we've got point P, and we're going around 90 degrees like that. So P started there, it will go there, then back to the beginning. So that's another order of 4. Now, there's tons of rotational symmetry logos, all right? The number 1 is the Star of David. Number 2 is like the nuclear system and all that sort of thing, okay? So let's try some of these examples. Okay, so if I was going to do this one, I would say, okay, I'm going to start here, and I'm going to assume, boom, that if I go around the clock, so 1, 2, 3, 4, 5, 6. So we're saying number 1 has an order, a rotational order of 6. Okay, and number 2, what do we think? Well, if I go there and go around the clock, so that's 1, 2, 3. So 1, 2, 3, 4. So number 2 has a rotational order of 4. Boy, my 6 really does not look good. Doesn't look healthy. Okay, number 3. Let's see. So we don't have to start at the top, but I'm going to go from that corner to that corner to that corner. So number 3 is 3. And number 4, let's say I start at this end right there. Nothing's going to happen up here, but it's going to happen when I get over to there. So that's 1. And then all the way over there is 2. So I'm going to say number 4 is 2. Look at number 5. The arrow starts there, and it's going to take all the way of going around to getting back to there. So I'm going to say number 5 would have just 1 order of rotational symmetry. Anyway, let's say how we did. We can go through all of those, and you can give them a try in a bit. But let's see what we got here. I put the answers over here. Make this a little lower, or smaller, sorry. Okay, and we'll get rid of all this junk. Boy, the magic of whiteboard, hey? Okay, so number 1 was an order of 6. Did we get it right? Yes, we did. A plus for us. Number 2 was an order of 2. But we said an order of 4. Well, what happened? See, here, black has to fall onto black. If I rotate it down here, it doesn't matter that it's still the same shape. It has to be the same color. So black can only fall onto black there. That's 1. And then there again. So that's 2. So we were wrong. Bad math teacher. Bad. Okay, number 3 was order 3. We got that right. Looking good. Number 4 was order 2. We got that right. Looking good. Everybody's kind of forgetting about number 2 when we got it so wrong. Number 5 was an order of 1. We got that right. We've redeemed ourselves. We're on the way. Number 6 is 3. 7 is an order of 2. 8 is order of 5, and so on and so on. So hopefully you get the idea, folks, that for a rotation to work, the shape has to fit and the color has to fit as well. Good. All right. Now let's go back to what we know here. So if we know that an object or an image has a rotational order of 4, can we determine the angle at which it will reflect on itself as it rotates? I mean, can we do the math instead of the drawing? Yeah, I know drawing's a lot of fun, but you have to be super accurate with the drawing. The thing is, when you get into big stuff like space stations and, airplanes and stuff, sometimes you got to do the math. Anyway, we can. So this is called the angle of rotational symmetry. When we say angle, we mean that we can figure out exactly at what angle it's going to work. Okay, now, if we look at this pentagon, it's got 5 sides, or 5 points. 1, 2, 3, 4, 5. And from this central point, we can see that as we go around, it's going to reflect onto itself 5 times. Okay, so basically, the angle of order of rotation is 360 degrees divided by 5. So so that means right down here, this angle is going to be 72 degrees. So every 72 degrees, we're going to get a symmetrical figure, and not before and not after, every 72 degrees. Well, that's pretty cool, but does it really work? Because the one thing we always say in math class is, we always want to say, how is it that you know this? How do we know you're not just feeding us a load of malarkey? Well, let's try it. Here we've got a Ferris wheel, all right? Now, if we look at this Ferris wheel, what we want to do is we want to count how many chairs are. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so kind of like the numbers on a clock. There's 12, all right? And there's our center of rotation. So we're not going to draw this Ferris wheel and rotate it over itself. I mean, we could, but let's pretend it's a real Ferris wheel, okay? So the order of rotation of this Ferris wheel is, whoops, let's change pens there. Good. Go back to a pen, go there, pen, is 12. Okay? Now, so to get the angle of rotation, basically what we're going to do is we're going to go 360 degrees, divide it by 12, because we're saying there's 12 points, and 360 divided by 12, grab my ever-present calculator, equals 30 degrees. 30 degrees. Well, what does that mean? Well, that means if we want to measure from this one to this one, as like, for example, the Ferris wheel has just gone up and your friends are waving goodbye at you, or they're spitting on the crowd or whatever, and it's gone up, and somebody says to you, hey, future engineer guy, what angle do you suppose that is? And you can say, it's exactly 30 degrees. And they would say, ha, prove it. Wow, check this out, guys. Let's just erase some of this, get some of that green out of there. Let's make it less cluttered. And guess what? I happen to have a protractor here. Check it out. That's what I like about whiteboards, okay? I'll make it a little bit bigger. And what we're going to do is we're going to put the protractor on so that it's sitting from that center of rotation, right there. We're going to bring this guy down. So we're going to bring this guy up right there. We're going to be accurate. Okay. So we're going from the Ferris wheel seat that we had up to the next one, right? And let's get rid of some stuff here. Okay. Check this out, folks. We start at 0. So that's right there, that seat. And we're going to go up 10, 20, 30. And let's go right down. And guess what? Whoops. That's right. We're right on that seat. Oh, get out of the way there. We're right on that seat. Bring this guy back. Check it out. Whoops. Perfect. Oops. There we go. 30 degrees. Ha! Told you. So, now, some kids would say, okay, Mr. Chambers, that's great. I'm probably not going to carry a protractor with me to the fair. And if my friend said, what angle do you suppose that is? I'd probably look around for a new friend. But I get that the math works. But why am I going to use that? Well, the idea of measuring a central angle shows up in grade 11 essentials, which is all about being able to make polygons to fit together like the tiles on the floor, or on a ceiling, or on a wall, or it's really a cool idea to know for carpentry because we do so much in the way of tessellations and things like that. Okay? Now, the next thing we're going to talk about, we'll just extend this page, is a tessellation, and we'll just click here, and I just want to introduce you guys to a fellow named Escher. Okay, now basically Escher's a guy who back many years ago did a really unique form of art where he could make pictures from shapes that fit together but made a pleasing image. So for example, in this tessellation, we've got geese flying, and they're slowly turning into fish. Now, that's not rotational symmetry, and that's not, well, it's kind of symmetrical, but the idea is that there's a lot that we can do with um, symmetry, polygons, tessellations, all that sort of stuff. All right, so that's your third video. Bring it back up here. Hope you liked it. If you have any questions, make sure you email me, Mr. Chambers Explains, or I'm sorry, chambers.kevin@bsd.ca. Maybe I'll write it right here because, it's been a while since, or I'll put it right here. I'll go back to our there. There you go. Keep it real, folks. Real with math.